Hello, my name's Henry and I'm going to be presenting to you today on MIDAS Civil and its use in a recently completed project for a post-tensioned balanced cantilever. So what am I going to be talking to you about today? Well, first off, I'm going to start with who am I and why you should listen to me. I'm then going to move on and talk a little bit about the project, and then I'm going to explain a little about post-tension balanced cantilevers in case you're not familiar with it, and then I'm going to dive into the structural modelling of how the bridge was sort of designed and the details behind that. And then, because I happen to spend about 2-3 years on site actually watching this bridge get made, I can also talk to you about the construction challenges and how the modelling techniques that we used help resolve some of these quickly. Now, as I alluded to earlier, my name is Henry Still, and I am an engineer at AtkinsRéalis, based in the Cardiff office, if you ever want to come and find me. We have offices all over the place, but Cardiff is where I am based. So, how did I get there? Well, you probably noticed by my accent that I am in fact not Welsh. I grew up in Brighton and Hove and then moved to Swansea University to study civil engineering and to get my master's degree. Swansea University is actually the home of finite element method. In case you didn't know, it's where the researchers pioneered the approach, and as a result my course was very heavily focused on finite element method and its uses in engineering. So I was well versed and in a great position to utilise those skills that I'd learned. So part of my course involved a sandwich placement or a industry, and for that I got a placement at AtkinsRéalis in Cardiff, where just happened to be that a large tender was ongoing for works on a scheme in South Wales, which has, as it turns out, been the majority of my career for the past 5 years. Obviously, I must have done quite a good job on that tender phase because AtkinsRéalis invited me back once I graduated. And there, I started work as a graduate engineer on this post-tension balanced cantilever. And throughout time, I've worked on this and continued to be the main focus of sort of my career, and then eventually the lead engineer has left, which then meant I was perfectly placed to take over that role, especially as we moved to the construction phase on site, where I was then placed on site to watch it be constructed. So I know this bridge inside and out, and I can tell you most details without looking at any kind of drawing, and that's why I'm going to be presenting you today on how we modelled it and how it's designed, and then the challenges that we've overcome. But before I get into all of that sort of juicy knowledge, I'm going to first talk to you a little bit about who AtkinsRéalis are. You might have heard of Atkins. Well, AtkinsRéalis is the result of a merger between S&C Lavalin and Atkins. We were sort of two brands under the same company for a while, and then we became AtkinsRéalis, and we are a large consultancy. We've got 38,000 people in 50 countries, and we were originally founded in 1911, and, well, we're engineering a better future for our planet and its people. It's a fantastic place to work, and we work on some really interesting schemes, which you might have heard of, such as like Heathrow's third runway, East-West Rail, and Hinkley and Sizewell C. So some very big projects. And then, of course, there is this project in South Wales. I think it's time to dive into what the project involved and some of the great engineering behind it. So, there was all sorts of challenges involved with the scheme. So it was an existing 3-lane road, in some cases it was just 1 lane, and it needed to become a full dual carriageway with grade separated junctions, which it didn't have before. But the terrain is immensely challenging. It's very hilly and very constrained in land take. So in places there is some deprived areas with houses very close to the carriageway, and in others we've got large sweeping hills and valleys. So all in all, some very complicated terrain and difficult challenges to work with, which resulted in 36 different bridges, involving some of the largest integral bridges that Atkins had designed, pushing close to 70 metres. There was then some typical, more standard pre-stressed beam bridges, again mostly integral, some on bank seats, some with integral abutments, somewhere on bearings, depending on where we're looking at. And then there were, of course, the post-tension balanced cantilever and an incredibly complicated widening scheme of a concrete arch bridge. It's all well and good me telling you how large and amazing the scheme is, but it's kind of useless unless I put some figures behind it. So overall, the scheme has been going on for 23 years, and they've spent £1.3 billion to achieve that, and it's a 45 kilometres of dualling scheme. Now, I haven't worked on it for 23 years, because I didn't start on this when I was 6. Instead, I've actually been working on the last section to be complete, as it's been done in phases. Now, the last section, as I said earlier, contains 40 bridges. I said 36, but that's because it's 36 new bridges and 4 refurbished ones. So I was also involved in those refurbishments, but most people are interested in the new bridges. It's typically what I find. And that cost £500 million and is 18 kilometres in length. And interestingly, it's been delivered under the mutual investment model, which brings about its own sort of unique challenges, but also some significant benefits to the taxpayer in the way that it is funded. So, without going too much depth into that, I'm going to move into the main star of the show for today, which is the post-tensioned balanced cantilever. Due to the nature of the scheme, it required a complex bridge in a complex location. So, the whole point of the scheme was to introduce grade-separated junctions and a free-flowing dual carriageway. So this required a key intersection between a large road going north into the Brecon Beacons National Park and the main road that's running east to west to have a key grade separated junction. Now this required, the post-tension balanced Cantilever Viaduct, but this means I needed to consider all sorts of challenges because both roads had to remain open during construction. So this design had to incorporate the fact that live traffic had to be maintained. It also needed to respect the fact that simply north to it is the Brecon Beacons National Park, with all sorts of the restrictions that come with that. To the south, there is I believe it's Grade 1 listed bridge structure, which is a fantastic masonry arch viaduct, really impressive, but I've got to do a post-tensioned balanced cantilever because no one will build a masonry arch like that anymore. But good reasons for that, which we'll get onto later. There is then also an existing post-tension bridge to the south, which we'll later find out was one of the key influences for some major design decisions. And then, of course, there is also multiple houses around the place, which need to be protected from, this huge bridge that's just ended up at the foot of their garden. So all in all, a lot of things to consider with the design and various challenges to overcome. This has led to what you see before you here. It's 180 metres in length with a maximum span of 75 metres. It stands 35 metres from the valley floor and has all sorts of interesting geometry going on. So we have an on-slip to the north, which curves on and then follows the curve of the bridge to the other way, so that changes not only in vertical alignment but also horizontal alignment as it goes along, and it merges with the eastbound carriageway just past the mid-span point of the bridge. There is also the fact that this is not just one post-tension balanced cantilever, but it's effectively 3 of them next to each other that then all get stitched together to form one larger bridge. There's also other strange oddities going on. So if you look at the abutments, you'll see that on the west side, it's just a pad foundation abutment, but on the east side, it needed to be piles. Various reasons for this. Mostly, it's just that's where the rock level was on one side compared to the other. So as a result, we have this rather interesting looking bridge model that needed to be designed. You will have noticed I've said post-tensioned balanced cantilever an awful lot so far, and if you're not up to speed in what they are, well, good news for you, I'm about to explain it. Simply put, post-tension balanced cantilevers is just a method of construction, and it does exactly what it says on the tin. So typically you build the piers, and then from there we build outwards from the piers in a mirrored fashion, creating your cantilevers. And key to keep them balanced, because it keeps your pier smaller than it has to be, trying to overturn those moments. So for that, you can either use precast segments, which are just lifted into place and then sort of stuck on, or you can pour in situ segments either side in a more sort of balanced way. And then typically, well, it's in the name, it's post-tensioned. So tendons are running through these segments, and they are either stressed at the end of segments going over the pier, or they can run all the way through the structure, or you might have some that just are in the bottom slab that stop and finish. Comes entirely down to the design. Quite a lot of freedom with the post-tensioning arrangement, but that's the overall gist of what they are. A key thing to note here is that the stressing sequence is key to the structure's strength. Obviously, as these cantilevers get larger and larger, there is an awful lot of moments there, particularly in hogging over the pier, and the post-tensioning is the key element that is able to overcome that. And then, of course, in the finished state, when the bridge is joined in the middle, that helps in the long-term design, and then you typically need some kind of tensioning in the bottom slab to help with the sagging case. This type of construction obviously means that the construction sequence becomes quite critical to the overall design. So, just to reiterate, typically you build the pier, you then construct the pier head and the diaphragm, you assemble your moving formwork, be it either travellers that move out from the pier, or something that spans over. There are some very fancy things used on high speed too, and I know other parts of the world use them, where they sort of span between the two piers and lift precast segments in. But in this case, we've got moving formwork where they get set up on the piers and then they just slowly move themselves upwards. And then you assemble the segments. That's simple. And of course, you cross your fingers and hope they meet in the middle. Because, of course, as these things move outwards, they start sagging, and that's going to require quite a bit of calculation to figure out where they're actually going to end up. And then, of course, with the pre-stressing, or with the post-tensioning, it's going to move the bridge again, sort of upwards or downwards, depending on which ones you're stressing up. So, all in all, quite a lot of stuff to consider. And obviously, the final case isn't always the most critical one. You might actually have an instance where the most critical case is during construction, which isn't always typical in most standard bridge design. Some pros and cons then, because everyone loves a good pros and cons list. So, why have we gone for a post-tension balanced cantilever? Well, some positives. They're incredibly efficient for 70 metre to about 300 metres, sort of their upper limit. I think some are pushing that now, but that's the typical sort of golden range for a post-tension balanced cantilever. They require very minimal formwork. You don't need a load of scaffolding. You just build your piers, you're typically using a slip form, and then from there you just build your travellers, which are quite straightforward, and you can work outwards from there. So minimal formwork is a great plus. They're ideal for difficult terrain. I don't need a load of columns, I can get away with just a couple. And all in all, that means that I don't need to have all sorts of difficult access arrangements from wherever I need to go. And then, of course, it's also actually quite a quick form of construction. At the peak, during construction, we were able to cast a new segment about 5 days, it worked out as, which means this bridge flew up. There are some negatives, though. Main one, I kind of alluded to it earlier, but the existing post-tensioned viaduct to the south was so good that they built it twice. Initially, they built the bridge, and then I believe it was precast, and what happened was, over time, road, salts and water got in through the joints due to the glue being poor. It then got into the tendons, corroded the tendons, and meant that the bridge had to be replaced after 20 years, which is not quite where we're aiming for. I want 100 years more than that. So, all in all, and various other cases like this, led to post-tensioned viaducts in the UK being banned. Thankfully, the rest of the world kept building them, and as a result, the better techniques were developed, designs for durability improved, and now they are no longer banned. Hooray! But it does mean that there's actually very limited experience of post-tension balanced cantilevers in the UK as of late. There's only been a couple before this, and this is one of the first ones to return. Another issue is that due to their construction sequence, they are quite a complex analysis, especially if you have different geometries going on, things being stitched together at different times. It creates quite a complex construction sequence that older software didn't really deal with. Thankfully, MIDAS Civil does, but it does mean that the analysis does have quite a bit of complexity in it. Certainly a 4D analysis considering time. And then the other negative is that key structural elements, mostly the post-tensioning, is hidden. It's not possible to inspect some of it without intrusive testing. So all in all, you are relying a bit on how well it was built and the durability design details. Another thing to consider is the time-dependent effects. So you have your classic key time-dependent effects, creep and shrinkage. There's also the tendon relaxations, which are happening with time. And because of the way these are constructed, every segment is a different age. Likewise, tendons are all stressed at different times under different conditions. And of course, as I said earlier, the deflections need to be managed quite carefully. This means there's an awful lot of time-dependent effects to be considered in the analysis, which you can do by hand, or you can make use of some software that has construction stage analysis. Now, the sequence which we considered was devised in collaboration between AtkinsRéalis and the primary contractor and their subcontractor, which specialises in post-tension balanced cantilevers. So, first off, we're going to build the on-slip deck. We're going to start with the east pier and then move on to the west pier and then join them up in the middle. Once that's done, they're going to move to the eastbound deck, which is going to repeat the exact same pattern. And once the eastbound deck is complete, that's going to then move to the westbound deck, which will be constructed third. We then deck stitch the on-slip and the eastbound decks together, which will then be followed by the wing on the eastbound carriageway, where the on-slip doesn't actually quite connect. And then to finish that off, we're then going to do the deck stitch between the eastbound and the westbound, which is the full length of the bridge deck. And then finally, last but not least, we're going to do the wing on the westbound deck. The reason for the wings is that because of the construction sequence, there is only 4 form travellers, of which they're all the same size, and as a result there is limitations in the sort of width that can do, and as a result the wings get cast as a separate traveller. So to recap what we've covered so far. We have a road scheme in South Wales with a load of bridges and some challenging terrain. We're building a new grade-separated junction, and the star of the show is this post-tensioned balanced cantilever. It's going to be built by constructing the piers first, and then working outwards from there using form travellers and in-situ segments. And to do that, we're going to consider all the various challenges that come with that, mostly the construction sequence. Obviously, we had to set the construction sequence in stone at the start because of the key influence it has to the analysis. So, we worked very closely with the contractor at the time to agree the various staging and when things will actually be built on site so that we had a basis from where to start the analysis. Let's talk software then. So, the modelling software was an easy choice and will come to no surprise to you given the whole agenda for today. It was MIDAS Civil. MIDAS Civil NX hadn't launched yet, so we're stuck on MIDAS Civil due to limitations of my time. And the main reasons for this is we needed the construction stages. We wanted a clear way to define the construction stages and work our way through it. I also wanted time-dependent materials to be considered in the model. This will help with calculations of pre-camber and the various things with that. And it's also very easy to model and refine tendons in MIDAS Civil, far more than some other software packages that I have used, and that is why we ended up on MIDAS Civil being the key software to analyse the structure. There were multiple models in they were developed, but the primary model and the modelling strategy for that was that we were going to consider these as, well, in an ideal world, it'd be a simple line beam. Unfortunately, due to the way that the bridge is, I can't just have a simple line beam. Instead, I have 3 adjacent line beam models, which will all be modelled in time, and then, of course, they will all have their tendons modelled. Once the viaducts have been completed, before they're stitched, it was just 3 line beams that just happened to be next to each other. The moment the stitches come together, the model becomes more like a grillage, so the transverse members start turning on, and then with that we have a simple, I call it simple, a complicated grillage model with various construction sequences, 2,000 or so elements, about the same number of nodes, and of course various tendons modelled and an incredible number of construction stages, all with the time-dependent effects considered in the model. And let's have a bit of a dive into the line beam itself. So here we've got the on-slip deck and its various sequences. I've cut a few out just because otherwise it wouldn't fit on the screen. But basically, build the piers, those segments turn on one by one, and then we start building outwards from there. There is, because this is an in-situ pour, we actually pour one side and then the following day we pour the other. So there is actually a small out-of-balance condition where you have one segment on one and not the other side. So key to consider for the piers on that one. But the key thing I wanted to get across with this is to reduce the number of construction stages in the model. What actually happens is all 3 line beams are, the on-slip eastbound and westbound, are built at the same time in the model, and then each segment, each viaduct, then gets a time case applied to it. This allows me to cut the number of construction stages by 3 effectively, which is ideal, and it also just made it a little simpler to clean up, just sort of manage the model, because we still have an incredible number of construction stages. Overall there's 72 segments, and then there's also the stitching and the various other sort of time steps that I need in there. So all in all, it's quite a complicated sequence, but I'm sure you figured that one out already. An interesting aspect of this type of construction is the form travellers themselves. So for this viaduct we had 4 custom form travellers that were made in Spain. They weigh about 90 tonnes each. They're all slightly different because of the segments they were casting, but pretty much the same. And they're able to self-lift and launch themselves. Very interesting to watch. You have to watch from a distance, you can't be near it whilst they're doing it, but it creates this interesting accidental case where if you've poured a segment and then you move one of the travellers and it falls off, you have to consider that. So quite interesting sort of thing that we have to consider in the model there, especially in the different construction stages due to that overturning forces that we need to consider. There is also the scaffolding for the backspans. So as you'll notice in some of these images, towards the abutments, the ground actually comes quite close to where the bridge is. So we're actually able to build those backspans on scaffolding. I believe this is quite typical for this sort of construction, but it just means that the formwork needs to be considered in the model as well, with the various boundary conditions that creates and the various large loads that are present when segments are cast. And then finally, the other thing to consider with the sequence is the closing sequence. So when you stitch these various cantilevers together with the other one, it locks in all your forces, which is absolutely key to the final design, especially in this case. It's actually asymmetrical. Typically you'd have a middle segment, or at least you'd aim to have a middle segment, which is your closing one. In this case, we actually have an even number of segments, and as a result, the closing segment either has to be on one side or the other. So in the diagram here, we're closing off the west side, then the centre, and then the east side, and that's locking in forces accordingly, and that is what the model was built to do. Now, I have 72 deck segments, and they're all cast in situ. Each segment is typically about 6.4 metres long. This is actually very long for a post-tension balance cantilever, but that is the size of the form traveller that was designed for it, so that is the size of segments. It does mean that the overturning force in the outer balance sequence is larger than it would otherwise be. It also comes with some interesting challenges. Basically, the tendons, particularly in the top slab, can only start and end at the end of a segment. This means that the tendons step down in force quite significantly at each segment, which isn't always ideal in the design that we have. And then, talking about the post-tensioning then, we have tendons in the top slab and some in the bottom slab. The tendon arrangement I'll get onto in a little bit. So how did I model it, you might ask? Well, thankfully MIDAS Civil comes with post-tensioning segment sort of wizard, so I don't even have to draw it in CAD. MIDAS Civil will do it for me. So it's quite simple. You just fill in the section data and out comes our lovely little model. Of course, it's you might have noticed it's a tapered section in cross-section, so that had to be considered, and also, every segment is actually a different size. One of the reasons why they're not precast and are in fact cast in situ is that they're pretty much all different due to the geometry. As a result, there's an awful lot of segments and an awful lot of taper groups that were made. But all in all, it's quite straightforward to just input that kind of data. Now, the middle closing segment is an interesting one. Basically, due to construction restrictions, it's not possible to pour that segment all in one like the other ones were made. Instead, what we have to do is pour the bottom slab and the webs. We can then remove the scaffolding from that and then pour the top slab. This means that we ended up with this two-stage composite element, which was, again, easily done in the section properties calculator that is present in MIDAS Civil. You'll also see there that there's a little I-beam on top. That's basically just to represent the travellers when they reach the middle, try and lock the two decks together. So we just have an element to represent that stiffness. On to the post-tensioning arrangement then. So it's quite a complex post-tensioning arrangement, mostly influenced by the segment sizes. So we have the top tendons. They're simply there for primarily during the construction stage, where the cantilevers are trying to sag downwards and those tendons haul it back up to the top. And then once the bridge is cast together in full, that helps with hogging over the pier in live load traffic cases. And then the tendons in the bottom are to help with the sagging cases. Obviously the intention of the tendons is to mirror that of the moment profile, but due to the construction stage, sometimes that's a little restricting, especially with segments this large. As a result, quite a lot of the bottom tendons are discontinuous rather than continue over the pier. That was mostly a designer's choice rather than sort of typical, but that's what we've ended up with here. This bridge is quite curvy, which means in plan the tendon arrangement is a little complicated, especially given some other restrictions. Basically, because of the huge force around the end of the anchors, end of the tendons, you need sufficient anchorage, and these anchors are quite large under the BBR post-tensioning system. Because of this, they can only be started and finished in certain places, particularly where the web is big enough. We were keen to keep the web as thin as possible, which means we can actually only... to keep the deck as thin as possible, which means we can only start and end tendons when they're over the web. So, as a result, there is this complicated fanning system where tendons sort of move their way outwards to end where they need to. This obviously has to be mirrored, which on a curve is quite difficult because I don't want to induce horizontal forces from that curvature. As a result, you get this sort of image you see on screen with the various different moving outwards, and as you can see, it does result in quite congested reinforcement around the anchors. This is something we actually later resolved on site with some tweaks, but a key thing to consider if you ever are doing one, it's probably best to offset your anchorage down so it's not in the top mat of reinforcement. So with all that complicated tendon arrangements and the many tendons that we have, how do I quickly put that into the model? Well, thankfully, Midas has done it again with the various tendon sort of profiles it lets you input. So the tendon properties, very simple. It can calculate the various relaxation coefficients, and the various other properties are input into the little wizard that you can see. And then the tendon profile, the way we've done this is first we drafted them in AutoCAD and then converted this to an Excel table. This was simply so we could play around with the arrangement, because obviously it's quite complicated. From there, we've taken the tables and pasted it straight into the profile tool. That saved an awful lot of time. And then we've repeated that 308 times. I have 308 different tendons in this model due to the various discontinuities going on. And as a result, we end up with that. So on to the stressing sequence then, which obviously has a large impact as well. So each tendon has a very specific time of when it should be stressed. Obviously the top ones get done first, and you can't stress the bottom ones until the bridge is actually completed. Obviously it goes through segments that aren't built yet. But because of the curves, the sequence has to be managed accordingly for that in just the top ones. So we can't go stressing a load of the outer ones on one side and then on the other, because the effects induced by the curve will cause all sorts of issues. So we have to devise a very specific sequencing step for those tendons, which we then put on the drawings to be followed, and all was good. And the key aspect of the design is that it's 3 viaducts that then get stitched together to form one large sort of intersection junction. Because of this, you need a traveller that is able to stitch the 2 decks together, which is shown on the screen here. It basically runs on 2 rails. It travels along and it pours, I think it's a 10-metre bay at a time, connecting the segments on either side together. Because of the way this bridge is, the different decks are at different ages and have a different amount of tendons stressed. This means that when they're stitched together, the age of the elements is quite key. We also needed to make sure that all the stressing had finished, so all the bottom tendons would have been fully stressed by the time that the decks become stitched. This is just to reduce the relative movement between the 2 decks. But of course, because they're different age, they're undergoing different creep and shrinkage and relaxation properties. So the stitch between them has to consider that in its design, where the forces were taken straight from the model due to the construction stages in there. As I keep alluding to, there is an awful lot of construction stages in this model, and I want you to take some time to have a guess at how many I've got, because I've got the 3 decks, I've got 308 different tendons, and then there is also the stitching sequence of the viaducts together, and then of course I also need different times afterwards to be checking the design at. So how many do you think there are? I don't have a license to the countdown clock music, so I'm just going to reveal it as 108 different construction stages, which is an awful lot, considering as most models I deal with will have 1 or maybe 2. So 108 is quite a challenge. Thankfully, Midas made this a little easier to manage due to the way it handles construction stages. So here you can see is the sort of construction stage interface in MIDAS Civil. I believe in NX this has got a facelift, but I haven't had a chance to use that yet. But so basically we've got the elements, the boundaries and the loads. So all the elements are activated when they need to be and then stay on and get brought in at different ages. Then the boundaries, I mean, they're quite straightforward. Only interesting ones here really are the scaffolding, basically being a one-way spring in that they couldn't stop uplift, but do certainly resist the downwards vertical motion. And then of course all the loads, so I have the travellers here represented as different vertical loads that come on and off at different stages, and then of course all the tendons and things make up other stages. But thankfully, due to various time load cases, that's helped reduce that down massively, so I don't need all sort of each deck modelled individually. Otherwise I would have like 3 times as many construction stages, which I certainly didn't want. A word of advice for anyone who might be considering doing one of these soon is don't change the construction sequence. That would be my overall #1 instruction to you. Mostly because to create the 108 different construction stages requires an awful lot of just sort of thinking and checking that everything is turned on and off at the right time and everything is considered at the right moment. So an awful lot of work goes into that, and it's the basis of the entire model, so you get that wrong and various results start going a little strange. So that would be my #1 tip: don't change the construction sequence. The model does also consider various moving loads. This was basically just done using the standard approach to moving loads in according to the Eurocode, using the moving load optimizer. We've defined the lanes as you typically would. Due to the geometry, there's actually 19 different vehicle lanes to check. And then there's the various vehicles, so we've got SV196 being the largest that this was designed for. And then using the MIDAS moving load case sort of wizard thing. I don't think it's called a wizard in this, but basically it creates the cases for you, combining the vehicles appropriately, and then that gives us moving loads. Now, due to the way it is sort of works in MIDAS, that checks every single node for every single thing, which on a model of this size with the various construction stages takes an incredibly long time to run. But thankfully, there is a way to resolve that problem. Without optimization, the model takes so long that it's basically unworkable. 9 hours is pretty much what it was taking, and that wasn't on a weak laptop either. That was a very powerful laptop running that, and it still took about 9 hours, which, when you make small little tweaks to like the tendon arrangement, that's quite a problem. So, thankfully, in the Analysis tab under Moving Load, there is all sorts of filters you can put on, where you can restrict it down to what you actually want to check. So we've created certain groups for elements that we're mostly interested in, and have run it accordingly. For sake of completeness, we did actually run it for everything at the end, just to see how much time it was saving, and it did cut it down by about a factor of 3. So after all that modelling wizardry, all I'm interested in really is the results output. And for this instance, a key thing that was an advantage to MIDAS Civil is that it will display stress results. So setting it up properly, you can get it to display your stress diagrams, which is key for our tendon arrangement. So there's various restrictions on tendons in that mostly they have to remain entirely in compression and you're not allowed tension around them. As a result, we are able to quickly refine where the tendons were based off of these stress diagrams. We can quite simply just look at it, see if there's any tension going on, and if there is, adjust the tendons around it accordingly. And what a lifesaver that is. That really saved an incredible amount of time. In terms of the more traditional sort of capacity checks, this was done in a more sort of, I guess, old school way, in that we created a load of fancy Excel spreadsheets where it was basically just checking through the properties and then determining what the capacity utilizations were. There is a quick way of doing this. In MIDAS Civil, there is the PSC design features. Due to contractual limitations, this wasn't an option for the project, but I believe that is a way forward if you're looking for a quick way to analyze segments and its reinforcement arrangement. Now, a key advantage of all these construction stages and the time analysis is the pre-camber results. So, as I said earlier, the deck moves with time due to the various forces it's experiencing, and then due to the various losses and creep and shrinkage, etc., this then moves it even more. So, part of the contract was that at the 5-year time period after completion, that the deck would be completely level, and for that we want pre-camber. So basically we're going to either build the deck slightly higher or slightly lower, according to how much we think it's going to move. And thankfully, MIDAS makes this very, very easy. Under the Results tab, there's a feature called Camber/Reaction, I believe it's called, and the tool will basically plot this graph for you. I've copied out the results table from it and just plugged it into our PowerPoint here to give us a pretty graph, but MIDAS will display a graph accordingly like this, and that in turn tells us how much each deck segment needs to be offset during construction, so that at 5 years it'll be beautifully level. Then, after all of that modelling, there are some limitations where it's not able to do quite what we're after. So there were a set of secondary models, mostly the abutments, which were modelled as 2D plates on one-way springs. Didn't need to be one-way springs, it's just how I modelled it at the time. But there was the abutment models, and then there was also a localised model for 2D which was again 2D plate elements to check the local effects. The way this one was done, as you can see on the screen there, it's the bottom image, is the density of the mesh is very fine, and the supports at either end were taken as an equivalent from the model. Rather than doing the whole thing as plates, it would take an incredibly long time to run just due to the number of elements. So as a result, we just did this sort of like 20-metre section and had equivalent supports to make sure that we got the local effects modelled appropriately. And then finally, there is also a natural frequency model, which you might be wondering why that exists. But basically, in the Euro codes for dynamic wind effects, this post-tension balance cantilever in its unfinished state, so when it's at maximum length, is a little susceptible to vortex shedding, which induces dynamic vibrations. Basically, this natural frequency model was to prove that, okay, it might vibrate a little, but the vibrations are actually so small and insignificant that the structure is completely fine with them. But that's a whole presentation in itself. So, all in all, that is the entirety of the modelling, its sort of primary and secondary models, and how the bridge was designed. So, with that, the drawings were produced, and it went to site, and I followed it there along with. And during construction, as an engineer, you will quickly learn that nothing quite goes to plan, and things that you never want to change end up having to change. So then, changing the construction sequence. Let me help you picture the scene then. So, construction has started, and as you can see in this photo, the east pier is at the stage where the hammerhead has been completed, and the west pier is currently at a stage where I believe they're moving on to segment 2 or segment 3. Originally, what should have been the case is the east pier should have been the one that was ahead, but due to excavation issues with the rock being at different levels to what was expected, the east side ended up behind schedule. A key thing with this structure is that it was on the critical path, and a 3-month delay would incur significant financial penalties. Being the budding young engineer I was at the time in my newly found sort of lead role of the structure, it was up to me to make sure that we could save that 3-month delay on programme by mirroring the construction sequence. Because the design is asymmetrical, this wasn't just a simple mirror, it actually changed which segment was the closing segment, particularly in the centre span this is, and also, obviously, it's changed the other ways, so the east is now last to be closed instead of first, and west is now first instead of last. And as a result, this did change the forces that were locked into the structure, which did mean that a structure that was already very highly utilised was now even more so. Thankfully still on the safe side after the various checks that were done, but it did mean that we needed to go through the model and basically mirror everything that has happened. This was a fair chunk of time, but not as much time as doing the whole bridge from scratch. Thankfully we had all the spreadsheets set up and things to quickly redo this, and it meant that in just a few weeks we were able to completely check the model check the bridge, I mean, using the model to confirm that the bridge was actually okay by being mirrored. And in turn, this did lead to some significant saving. It was able to claw back 3 months on schedule, and that is a huge amount of time to save during construction. Unfortunately, a consequence of this mirroring is that the pre-cambers that were already constructed on the segments that were finished at the time were wrong. They've been built slightly off because of this change. But thankfully, because we were near the pier, the the amount of precamber given to these isn't actually that significant, and due to some forward thinking in the early planning of design, we were able to take this out in changing to the surfacing level, which meant that this change was given the go-ahead in a very small time frame, and it did mean that we were able to get this constructed and claw back those 3 months. We did then have a very interesting request come in. Due to the way construction was progressing in on different other structures, a request came in to see if we could run traffic on the on-slip bridge deck before the rest of the bridge was completed. An interesting challenge, and it's not often you get asked to run traffic on a bridge that's not done yet. But again, due to the way the model was set up, we were able to just easily cut off when the construction stages were finished. You can do this in MIDAS by just telling it what construction stage is the last one, and it'll run accordingly. And then we ran the traffic loads on that and confirmed that the bridge, the temporary bearings were okay to withstand this kind of loading, which meant we were able to save even more time for the constructor in the construction of the rest of the scheme. Now, the big thing that these projects always lead to was it a success? So the various changes to the construction sequence after the fact did claw back 3 months. Running the traffic early did allow even more time saving in the surrounding area, which resulted to the bridge being finished early, which I know is sometimes almost unheard of. The budget was also met. Due to early contractor involvement, we saw off many issues long before they got to site, and in that close collaboration on site also helped things massively. We were able to solve things very quickly, and a large part of that was due to the flexibility of the MIDAS model and how easy it was to quickly change things and then run and get results. And then the big thing that would always cross my mind is what if these don't meet in the middle. Originally, we allowed a 10mm deviation, mostly in pitch, but thankfully the actual deviation achieved on site was only 1mm, which was a massive relief after the incorrect pre-cambers on the early segments. So, all in all, an all-round success that I think is one of those bridges that just looks remarkably impressive and is a feat of engineering. Even if it's not the world's biggest post-tension balance cantilever, it is at least the newest one in Wales. I really hope you found this presentation interesting, and the tale from the very beginning, and how it's developed in the design, and then how it went together on site and the various challenges that came up there. I'm incredibly passionate about this project. I very much see it as my baby, even if it's not. It's very much close to my heart, as it's been a large part of my career, and I've thoroughly enjoyed talking about it for you today. So on that note, I'm going to leave you with any questions, and I'll be happy to answer them.